Okay, so let's get on with lecture 37. Okay, so the material on this lecture will be the last of the material that will appear on exam 3. Okay, exam 3 covers lectures 25 through 37, which is this right here. After the break, we will have another lecture on 17. And then I'm thinking about giving like a review session right here for the final. That'll probably be more important than giving another lecture on 17. And so also this practice exam, remember, it's on the weekend before we get back. So it'll be that Sunday before this Monday right here. Okay. Yeah, and also this evening I gave you this last bit of homework on these couple of lectures that we just had as well. Okay. All right, so in review for our last lecture 36, so recall that the BJT behavior at high frequencies, it can be analyzed by calculating the frequency-dependent short circuit gain beta of S. So remember, this is the small signal hybrid pi model right here, and because we're dealing with high frequencies, the difference between the regular hybrid pi model and this high frequency one is that we're including these capacitances, C pi and C mu right here. So otherwise this right here will be an open circuit and this would be a short circuit. Okay. And to analyze that, what we do, we use this short circuit method to determine the gain beta. So we apply the short circuit right here for that current. And we also apply an input current right here. So that's the difference going from here to over here. And so what we found is that we're able to determine what this current gain right here is. And we do a Bode plot of that right here. So the blue line is this equation. And we can see as S, which is equal to I omega in this case, when omega goes to DC over here, this asymptotes to just beta 0, which on the log plot is 20 log beta 0 right here. And then at, so at this low frequency, beta 0 is the transconductance times the input resistance R pi. Okay. And at higher frequencies, what we find is that there's a single pole roll-off at 20 decibels per decade, and that's when you're having your frequencies much higher than your cutoff right here. Now at cutoff, at this frequency right here, remember that is 3 decibels down from the max amplitude. So the point where that happens is the cutoff, and that's determined by F beta or omega beta right there. The unity gain is the cross through, so when this keeps going down and crosses through 0 decibels, that's the unity gain at that point. And it is described like this, and omega t is the unity gain bandwidth product. And so this omega t is just your beta 0 multiplied by your cutoff frequency, omega beta right here. Okay, so that was our last analysis of looking at the high frequency characteristics. Okay, so in this lecture we'll look at high frequency of the common emitter and common source amplifiers. Okay, so continuing where we left off, first we were analyzing what the frequency response looks like for the simple RC, then we modified it. So let's look at that again. So if we look at the high frequency response, we're looking at Vx right here as output over the input Vi. So this Vx has the R2 in parallel with this C1. So right here is all Vx right here. And so by voltage division, we see that we have the resistance here is these two in parallel, right? So that's where we have the R2 multiplied by the impedance of this 1 over SC1 right here, divided by R1 plus this resistance right here in parallel. Okay, so that's what that is. And if we take this and work that out, we get this expression right here. And if we divide top and the bottom by this denominator, we get this expression. And the reason we're doing that is because we're trying to identify the terms. We want to identify this part as the A mid right here, and this part as the high frequency component, which is a function of S. So that's what we have here, where in this case we've taken the S and substituted in omega J, or J omega, and that's what this is right here. And so that's how we identify these parts for the high frequency component. And it looks like this, where here's the A mid part, and then it falls off right here at that slope. Okay, and you can clearly see here that when this goes to DC, when that goes to 0, this goes to 1, and all we have left is this right here, which is the A mid part. And here's the phase diagram right here, phase as a function of frequency. Now, to make the modification for some further analysis, and this is getting into the Miller effect, what we did, we had taken our RC circuit, right, and we added onto it this piece right here in this red block. So it consists of an amplifier with this capacitor as feedback. So this capacitor is CXY, okay? So in doing so, we want to try to find an equivalent capacitor of this and find out what the relationship is between this equivalent capacitance and this capacitance right here. Okay, so in doing so, the image of that is right here. So this circuit right here is going to be replaced with this circuit right here, where this C equivalent is the same thing as, or has the same effect as what's happening here, where this capacitor right here is the feedback. And the reason we're doing that is because we want to be able to break apart components of these networks. And that's the reason for doing that. So that's why I want to analyze that and get an expression for this in terms of that. Okay, but these two circuits, if you look at them from the outside, right, and treat them as a black box, you can't tell which is which if you do this method. Okay, so we'll calculate the equivalent input capacitance, CEQ, by finding the current going through the capacitor CXY, this current right here, IC, from this node. And so let's first look at the admittance. So the admittance, YS, is IC, this current right here, divided by Vx, which is the voltage right here. Okay, so this current IC is equal to this conductance multiplied by the voltages across the capacitor. So here's Vx, and here's Vy right here. So that's what IC is. And Vy, if we look at that as your amplifier, that's just your gain, AXY, multiplied by Vx at the input. Okay, so substituting that into here and pulling out the Vx and substituting this into here, the Vx's will cancel, and then we get this expression right here. Okay, and here's what we do. We identify this piece right here as your equivalent capacitor here. Okay, so again, the admittance right here is seen from this direction and that's the input, or it's the output of this going into the input of that, right? So it looks like this in this circuit, which is equivalent to this right here in that circuit over there. Okay. And so here's the salient expression right there. And you can see what it's doing too. You can see the effect of the amplifier's gain onto this right here. So C equivalent is just your capacitor, your feedback capacitor, CXY, multiplied by this right here. So it's 1 minus whatever the gain is. And that's what the equivalent capacitance is right here. Okay, so yeah, so this amplifier gain, AXY, it actually produces an effective capacitance at its input right here. And so this CXY is just scaled by this factor. And this scaling factor, that is what is called the Miller effect. Or it's also called the Miller multiplication. Okay, it's this scaling factor right here that's being multiplied by the capacitor due to that. Okay, so so let's look at the Miller effect a little bit more. So let's look at the high frequency transfer characteristic. So we'll compare the RC circuit, compare it to the RC right here, plus this part right here which contributes to the Miller effect. Okay, so for RC, remember, this is what we had right here, and we ended up with this, and we had broken that up into A mid and also FH, which was 1 at low frequencies, and then it fell off after the cutoff. And so the difference between these is that this R2, you can think of it as being replaced by this R2, which is in parallel with Rn. And Rn is seen right here. So yeah, this R2 in parallel with that Rn. And so here you see I have another R2. That's going to be in parallel with Rn. And this expression on the bottom right here is, well, again, you have this R2 in parallel with Rn. That's there. But this piece right here, this C1 right here, is being now added with this other one that's in parallel to it, the equivalent C that we got. So this feedback capacitor, CXY, is now can be represented like this. And so now these two right here could just be added together. So that's where this comes from, right here. Okay. So now the pole frequency. So it's determined by the resistance, where you have R1, which is in parallel with R2 and Rn, and this capacitance, which is C1 plus C equivalent. Or here's this CXY plus this scaling here. So let's look at a couple of examples. I put the circuit here so you can see the difference between this one, which is the SC equivalent, and this one, which is the CXY. So for example, let's say the gain, this AXY right here, was negative 10. And so the input capacitance due to CXY right here will be the C equivalent, which is, so this C equivalent is going to be multiplied or scaled by a factor of 11, right? Because if you put like a negative 10 right here, it's just 1 minus negative 10, so that's where you're getting the 11 from. So that's a huge scaling right here. So now if your voltage Vx right here was just 10 millivolts, then Vy will be 100 millivolts, and Vc across your CXY, this Vc right here across that, will be 110 millivolts, right? So you're starting at 10 millivolts, and you're going downhill 110, so you end up at negative 100 millivolts. Okay, that's where that comes from. So, so if you want to think about it, as the voltage at the input of the capacitor, right here, is increasing, the other terminal is rapidly decreasing. So increasing right here, the voltage at this other terminal right here is rapidly decreasing. And that's causing the driving circuit right here to deliver a much greater current than would be expected given the actual value of that capacitor, which is this one right here. Okay? That's pretty interesting. Another way of thinking of it is if you have, let's say you have a much lower gain. So instead of like, a magnitude of 10, let's say you have this 0.9 instead. You end up with an equivalent capacitance of just like just 10% of CY, right? So it's order of magnitude less, okay? Which yields a much smaller current from the driving circuit. So what you could take away from that is that this Miller effect, what it does, it allows us to separate capacitively coupled sections, okay, with this right here, of a circuit into simpler RC circuits. And in doing so, that's actually much easier to analyze if you do it that way. So that's the benefit of the Miller effect. Okay, so let's look at common emitter and common source amplifier and a high frequency response with that. So here's a common emitter amplifier, okay? And we can transform that into its high frequency AC model, okay? And this RB right here is going to be, remember that goes to ground, so this RB is going to be the R1 and the R2 in parallel, right? That's shorted right here. This remains, that's part of the load, and this right here is bypass. So these two are coupled. This is a bypass capacitor right there. That's why we just have this. Okay, so in this common emitter amplifier with low frequency coupling and bypass capacitors, the C1, C2, those are the coupling, and C3, that's the bypass. So now we'll consider the high frequency response. So we'll consider the low frequency capacitors to be open circuits at DC and short circuits at mid-band and high frequencies. This CL right here represents the high frequency low capacitance, and we'll calculate the mid-band gain and use the Miller effect to calculate the equivalent capacitance at the input, okay, which is right here. Okay, so the mid-band input gain is this. So it's the ratio of, in this case, the output is VB over VI. So here's VB right here, here and here. Here's VI. So this is the input gain going into that to there, and we've seen this in another lecture where it's this expression right here. And remember what Rx is, right? That is that extra resistance when you for this current going in from the base. Do I have a picture of that? I don't have a picture of that. Okay, but last time I showed like a physical drawing of this transistor, and that current actually goes through some material, and it's at a pretty high resistance before it gets to the active region. So that's what this base resistance right here is, that Rx. Okay, and so the terminal gain is just VC over VB. Here's VC here, here's VB, and we've seen before that this is negative transconductance times RL, and you can estimate it to be like this if you assume that R0 is going to be pretty high, the output resistance. Okay, so now let's use this Miller effect to calculate the input frequency pole at the base. So this piece right here, we're going to replace it with this. Okay, so here you have your Ri and Rb. That's these right here. And we'll take this and replace it with a small frequency model, right, where it's linearized right here. We're including these capacitors. So we have the high frequency hybrid pi model. We're including the input resistance and also the base resistance. We're neglecting the output resistance, RO. okay? But remember, again, that's from our frequency-dependent hybrid pi model, this piece right here. But we just add the Rx coming into that. Okay. So, so first, let's look at the equivalent capacitance at node B. That's this node right here. Okay, so now we see that we have two capacitors. We have this C pi and also C mu. So if we apply the Miller effect, which means that they're going to be scaling, they're going to be scaled by some amplification, then we'd write it like this. So this C mu is being scaled, some equivalent capacitor, meaning that we're going to take the C mu and put it in parallel along here as some equivalent capacitor. That would be written as 1 minus some amplification gain right here, which is A, B, C. Now, in this case, A between the base and collector is this, negative GM RL. That's what that is. Doing this, the equivalent, we don't have to write this, but I think the book wants to make a point that you can apply this to other capacitors. This C pi right here, that's being scaled by 1 minus this ABE. This part right here is 0, so we didn't really need that scaling, but that's between the base and the emitter, that gain. So this right here can be rewritten like this, right? We're just plugging these values in, and then written like that. Okay, so now that's looking at that direction. Now for this right here, we can do like sort of like a Thevenin-Norton type of equivalent type of thing, and we can reduce all these resistances into this R pi 0 and turn this into this current right here. Okay, so that's what we're doing here to simplify things. So yeah, so this R pi 0 right here, you could think of it as this right here, where you have this R pi, and that's being in parallel with Rx plus Rb in parallel with Ri. Okay, so Ri, Rb, these are in parallel. Like if you don't look at the, if you're turning this off, these two are in parallel. So it's this in parallel with that plus these two in parallel. That's where this expression comes from right here. And this expression is just your R pi 0. That's what that is. Okay, so we're going to rewrite this as this schematic right here. Now the time constant, if you remember before how we did the omega L, it was like the omega, the frequency at the low cutoff, it was 1 divided by all the RCs. That's what this is, all the time constants. So in this case, it'll be this R equivalent right here multiplied by this, the equivalent capacitor, which we calculated right there. That's what that is. And we need that for omega H, which is a high frequency cutoff. Now, at the collector output node, REQC, that's just going to be RL right here. And remember, this RL, it has all this other stuff thrown into there. It has the small signal output resistance, and it has the RC and R3. And I have a picture of that. But yeah, so here's R3 right here. Here's RC. Remember, these two go in parallel because that goes to ground. So these two become in parallel, and that's short-circuited. Okay. So that's where that comes from. And this is an approximation because you're not including the R0. You're thinking that's like really large, so most of the current will go through these guys. All right, and so the equivalent capacitance at the output node is actually this, and you'll notice that there's no Miller effect. There's no scaling. And that's because the Miller effect works in this direction, but not in the other direction from the output. Okay, so the same thing doesn't apply there. Okay, so no scaling with those. So you have the C mu and CL, these two guys. And so the time constant is just these two right here for that time constant. So now here's a few other things to consider. If the input and output nodes are isolated, then we'd find separate pole frequencies due to input and output time constants. You know, like if this time constant was different than this one, which they are, but if they were isolated, then we would do that separately. There would be no interaction. But in this particular circuit right here, they're coupled through this. Like this part is coupled through this part over here through that C mu. And also it says here that the input and output impedances are large, so the two time constants will interact. And so that's going to yield a dominant pole frequency that looks like this, right? So it's like this dominant pole frequency is 1 over the sum of these RCs. And so remember, here's the RC we computed first. Here's plus the other RC we computed second. And so here's the equivalent R. Remember that R pi 0 was where was that? I think I passed it up. Okay, well this is R pi 0, all this right here, okay? Yeah, there it goes. And also this right here. So that's where that first part came from. This part is R pi 0. This part right here was that other expression. And then what we just did before for the tau C, we have the RL, which is all the outputs in parallel with the equivalent C right here, and there's no Miller effect for that. Okay, so that's what that is. And so that's going to be the high frequency pole. Okay, so looking at this, the estimation of omega h using the open circuit time constant method, this is going to be very similar to the other one that we saw 2 lectures ago, where we had taken all of the capacitors, if you recall, and we made them all short circuits, and then we looked at that one capacitor, we took it out, and we found the equivalent resistance. We're going to do the same here, except now all the capacitors, instead of making them short circuits, we're going to make them open circuits. Okay? So the last one was for omega L, the low frequency cutoff. This will be for omega H, the high frequency cutoff. Okay, so it says here that the method for estimating omega H is similar to the short circuit time constant method, which we talked about last time, SCTC, used for omega L. The difference is that the upper cutoff frequency, omega H, is found by calculating the open circuit time constants associated with various device capacitances, rather than the short circuit time constants associated with the coupling and bypass capacitors. So at high frequencies, impedances of the coupling and bypass capacitors are negligibly small, and they can be represented as short circuits. However, the impedances of device capacitances have now become small enough that they can no longer be neglected with respect to the internal resistances of the transistors. Okay, so now the book didn't derive this, okay, but it says that it can be shown that omega H is of this form. And as you can see, the form is pretty much identical to omega L. The means of these things are, the method to determine the RCs are different. Okay, it's open instead of shorted. These capacitances, but the form of the equation is the same. Okay, so these RIOs, they represent the resistances measured at the terminals of capacitor CIs, with the other capacitors as open instead of shorted. So let's look at an example of this. So here's our model right here. Okay. Now for this first one right here, C pi, we'll find that and replace it. So we'll find the R from that, right? So we do this by removing this, looking at the resistance, seeing what is gone, and all the other ones, this one and that one, become open. So that's why you have no connection across here, and this bypass, this capacitor in parallel with that is no longer here. Okay, so that's how to find the first one. For this one right here, for this one right here, this is now seen as the resistance looking in, RLO, and these two become open. So this becomes open right here, and this just becomes open, just stays open right there. And you look at the resistance here. And for this one, C mu, you're looking at the resistance seen from this point, and this C pi stays open. So all you have here is just this resistor right here. And remember, the resistance of a current source is what? Remember what that is? That's going to be like infinite, right? The resistance of a current source. So that's why there's nothing there, or in this case, over there either. So, so you find the resistance looking in there, here, and also here. And so what the form of that equation looks like is just like this. It's whatever resistance you see looking into those parts with the capacitor gone, multiplied by the capacitor you have removed to look at the resistor, plus the next one, and plus the other resistor. So we have three capacitors, and so we have three terms right here, and that's going to be used to determine what this high frequency value is. Okay, so now determining this one is easy, right? Determining that one is easy, but that one right here is a little more complicated. Yeah, so this one right here is just this resistance right here, R pi 0. And this one right here is kind of easy too, right? Looking in this direction, the resistance is just this right here. But for this right here, it's a little more complicated because what you want to do is have this Vx over Ix, okay, and determine what that is. So you're going to have to create your Vx. Okay, so you do that by inserting a current source, this fictitious current source right here, to basically turn everything on to see what the resistance would be. Okay, so doing KVL, right, you can go around this loop. So this Vx right here across that is equal to the drop across here, and also the drop across here. So you have this IL going through here, okay? And the thing is you can pick any loop you want. So you're not going through this loop right here. Pick any loop you want as long as you get back to where you started from. And what this IL is, this IL can be replaced with this IX plus GM times V, right? So what IL is right here is this IX, so it's going through right here, this is IX, and this right here is GMV going down here. So that's just KVL to get that. Okay, so plugging this into here, we have this Vx, you substitute that in there, and then you have this Ix that appears here and here, and you get this expression, and you can reduce it to that right there. Okay, so so for the last slide right here, here's what we have for the frequency at high cutoff. So finding these two were quite easy right here. We found out that this right here were these two guys, but this last one, I'm sorry, this one and this one were easy to find, but this last one, it took some work, and that's what this is right here. Okay? And what you can do, you can reduce this to this expression, and this CT is what you get if you factor out this R pi 0. Remember, R pi 0 is right here, which was, let's put it back there, which is all this stuff. All this stuff is R pi 0 from your input. Okay, so if you factor that out, you can factor this out here, here. That one right there will end up being RL over R pi 0, right? But then everything else that's left over, if you group that together, you can call that your CT. Okay? All right, any questions? Yes?
When will the practice exam be available?
Oh, yeah, so that's going to be, since we'll have the practice exam on the Sunday before we get back, I should at least have it ready by that Saturday, the day before. I mean, there's no reason why I can't give it earlier. I mean, like, post it earlier. Did you want it earlier?
Earlier would be really good.
Okay, yeah, I could do that. Yeah, okay, I could do that. It's not a problem. I could, yeah, since we have all this extra time right here. Oh, I forgot about the time. Yeah, so let's decide on the time before the before the break. All right, so should we do 3 o'clock again on Sunday? You guys like 3? Anyone cannot make 3 on Sunday after next Sunday? You still be out of town? Okay, so let's make it at 3 again for that Sunday before we get back. Okay. All right, I'll see you guys in a couple of weeks. Have a great Thanksgiving break.